Okay, so if we carry on with these lectures, looking at reaction mechanisms. In the last lecture, we had introduced SN1 and SN2 mechanisms, and we'd looked at the difference between them. So what we're going to do now, is to look at a couple of specific examples of SN2 reactions. And I've chosen particular examples which will give you a chance to see where these reactions have been used in drug design and synthesis. So here, what we've got is a molecule which looks pretty complicated. There's probably some groups you've never heard of, like trityl groups. Don't worry about any of those. What we're looking at is this centre here, which has got a carbon with a leaving group. So if we've got a carbon with a leaving group, we know that this can be prone to nucleophilic substitution reactions. And we're told specifically here that we're looking at an SN2 reaction. So remember, that would mean substitution, nucleophilic, bimolecular. So if it's bimolecular, we're going to have two species which are involved in the rate determining step. We're going to have our molecule with the leaving group, and we're also going to have a nucleophile. So in this here, where we've got the reagents that are going to be involved in the reaction, we've got some heat to make the reaction occur, we've got a solvent to dissolve our molecules in, and we've got this, we've got a lithium, and N3 is azide. It's probably not a functional group you've come across before, but it's one which is very useful for introducing nitrogen into molecules. So if we know lithium tends to be plus, then that would tell us that this N3, the azide, is going to be minus. And so if it's minus, it's likely to be a nucleophile. So what we're seeing in this reaction is the N3 minus is going to be a nucleophile, which is going to come round and attack on the carbon at the same time as the leaving group departs. Now, you might not be able to predict from looking at the substrate whether it's going to do SN1 or SN2, but note it's telling you it's an example of an SN2 reaction. So if it's an SN2 reaction, our nucleophile is going to do the substitution at the same time as the leaving group departs. So essentially this comes round and attacks at the same time as the leaving group departs. Now the important point to remember from the SN2 reaction is the stereochemistry gives us an inverted product. So if you remember, because the nucleophile is attacking at the same time as the leaving group departs, we get inversion of stereochemistry. And that's shown quite clearly in the product, because here we've got this sticking up, pointing up in 3D space. Here our N3, our azide, is pointing down. So we've got inversion going from this centre here through to this centre here. That was important to know which stereochemistry we're going to get at this position, because when this was taken through in multiple steps, we don't need to worry about how it was taken through. But when it was taken through in multiple steps to this end product, we needed this to still be in the down position. So for it to be in the down position here, it had to be in the down position here. And the way to get that in the down position from a molecule which has the leaving group in the up position is to do a reaction that would cause inversion. And we know from what we learned last time that the SN2 reaction is the nucleophilic substitution reaction that gives us inversion of stereochemistry. Now, this particular molecule here is being very useful in the treatment of viral diseases. Don't need to worry too much about that, but it's useful as an antiviral. It can also be used in some cases as an anti-cancer agent. So it's a real example of where this SN2 reaction has been involved in the synthesis of a drug which has got therapeutic properties. Now again, I have prepared sort of a walkthrough video for this where you can see me sort of drawing in real time how this is reacting. So if any of this slide isn't clear, then have a look at that and you'll be able to go through it again with me drawing things out in real time. Okay, so that was an example of an SN2 reaction. Again, just to be clear, you would never have to draw this out, but if a scheme such as this was given to you, then you should be able to rationalize, why is it an SN2 reaction in terms of, we've got a molecule here, we've got this attacking at the same time as the leaving group departs. That's why it's SN2, and you should be able to recognize the stereochemical consequences of that. So if the leaving group was up, our azide is now going to be down. Okay, so another example for you to try, and in this case I have given you sort of an exercise to go through to see how you're getting on with this material. So this is another example of an SN2 reaction, and it looks probably pretty terrifying to you if you look at the different species and trying to work out what's going on. So what I've tried to do is break it down into steps for you. So I want you in this exercise to look at this molecule here, and I want you to work out in that molecule where is the nucleophilic centre, so where is the area which is electron rich. I also want you to think where is an electrophilic centre, so something which is deficient in electrons is going to be the electrophilic centre. I also want you to think what is the leaving group. So for this first step with this molecule here, which part of the molecule is the nucleophile, which part is the electrophile, and where is the leaving group? Okay, the reason again we've got this is because this is important mechanism by which an intermediate is formed, which can have well, it can be very useful in the targeted treatment of cancer. So the reason that this is useful in the targeted treatment of cancer is that this intermediate here, it's got a 3-membered ring with a positive charge. This is going to be incredibly reactive. It's going to want to react with something which is electron rich to open up this 3-membered ring and to feed electrons into the positive centre. And the nucleophile that can do this in biological systems is the DNA. So we've got very rich electron areas within the DNA in the base pairs, and they can interact with this in such a way that we can form this product. Now this can then go on to form another reactive intermediate by the same process that you're going to look at in the first step here. And this again is extremely reactive, and so the second strand of the DNA is again electron rich, and that can interact with this to give this product here. So once this has happened, it's really it's altered the DNA within the tumour. It's stopped the DNA from being able to unwind. If it can't unwind, then we can't get any transcription occurring, we can't get DNA replication, and that will effectively stop the tumour from being able to replicate. And if we can stop that, then we can stop the tumour from developing, and that can be an effective anti-cancer therapy. So you wouldn't need to worry too much about these steps from a mechanism point of view. I'm just trying to put the work in context so you can see how a knowledge of these mechanisms can help us to design molecules that can be effective in therapies. But what I do want you to be able to do is to work out what's happening in this first step. Where's the nucleophile, where's the electrophilic centre, where's the leaving group? Have a go at that, and then go through the accompanying video, which will go through the answer, and it will also show you the specific mechanism by which this reacts in an SN2 reaction to give this intermediate. Okay, so hopefully that's given you a few things to think about and an exercise to try out, and the answers are on Blackboard for you in this video here. Okay, so why does it actually matter whether we're going to be thinking about SN1 or SN2 reactions? Well, we've pretty much touched on this already when we've gone through the differences between SN1 and SN2. The reason it matters is because of the stereochemical outcome, the stereochemical consequence. Because in the SN1 reaction, where we've got our planar carbocation that we can attack via either side with the nucleophile, if we attack from either side with equal probability, we're going to get a racemic mixture. We will not get single isomers, we'll get a racemic mixture, which is an equal mixture of the two different enantiomers. If we do the SN2 reaction, we've seen we get the inversion, we're going to get a single isomer. So this is important because, as I've said before, if you had a particular drug as a particular isomer and you needed that particular isomer for the correct therapeutic endpoint, then you'd want to be using a reaction that only gives you that isomer, and we could use the SN2 reaction. If instead it was much more of a sort of discovery program and we didn't know which isomer we wanted, and so we were happy to have a racemic mixture and then try and separate out the enantiomers and look at them separately, then in those cases we could use the SN1 reaction. So dependent on the needs of the drug that we're making or we're researching, we would be able to pick the SN1 or the SN2 reaction. So if you're happy that it does matter whether we're going to have the SN1 or the SN2 based on the stereochemical consequences, then the next logical thing to think about would be, well, if we know we want one over the other, so maybe we want SN1 over SN2 or vice versa, we would then be wanting to think, well, what reaction conditions might we need to actually alter the reaction so we get more of the SN1 or we get more of the SN2. So the next thing we're going to look at are the factors that will actually influence whether the reaction proceeds via the SN1 or the SN2 pathway. This very much centres on the mechanisms that we've looked at, the mechanistic processes, the order in which the bonds break and they form. And we're going to see in the next few slides that there's a few things we can think about that will influence whether the reaction occurs via the SN1 or the SN2 pathway. So the first thing we're going to look at is the nature of the carbocation, because if that's stable, then it's more likely to occur via the SN1 reaction. We're going to look at steric effects. So steric is just the influence of different sizes of groups around the substrate. We're going to look at the nature of the nucleophile. So remember, that's the electron-rich, maybe negatively charged or a lone pair of electrons. It's that species which is involved in the reaction. We're going to look at the nature of the leaving group. So that's the group that breaks off of the substrate. And we're going to look at the nature of the solvent. So the solvent is the medium in which we dissolve our reactants to get the reaction to occur. So we look at these one point after the other. So the first thing we'll look at is the nature of the carbocation. So remember, the SN1 reaction occurs via a carbocation. So if we can form a stable carbocation, that's going to be favoured and the SN1 reaction will occur. If we can't form a stable carbocation, then the molecule isn't going to want to lose its leaving group to give the carbocation. And in that case, the SN1 reaction won't be favoured, and it's more likely the molecule will react via an SN2 reaction. So if we're thinking about the likelihood of the SN1 being based on the stability of the carbocation, we need to think what makes a carbocation stable. And the order of carbocation stability is that a primary carbocation is less stable than a secondary, which is less stable than a tertiary. And this is due to a phenomenon called hyperconjugation. So in hyperconjugation, we get donation of electron density towards that positive area of the molecule through the sigma bond framework, so through the single bonds. So wherever you've got single bonds, you've got electrons, and that electron density can stabilise the positive charge. So the more single bonds that you have, the more stable that carbocation will be. So a tertiary carbocation is going to have more single bonds than a secondary, which will have more than a primary. So that means that the tertiary carbocation has got more electrons to stabilise the positive charge than the secondary than the primary, which means that that tertiary will be more stable in the carbocation form than the secondary than the primary. So if we've got an SN1 reaction and it can form a stable carbocation, i.e. probably a tertiary carbocation, then it's likely to occur by an SN1 reaction where the leaving group will depart to give that stable positively charged carbocation. So hyperconjugation is an important phenomenon which can account for the extra stability of tertiary carbocations compared to secondary, compared to primary. We can also get stabilisation though through other groups. So you might have come across resonance. So resonance is where we can get stabilisation of positive charges through the pi framework, so through double bonds. So again, if you had a molecule which had a double bond in which was adjacent to the positive charge of a carbocation, that would be stable, and that would be another reason why that molecule which can form that stable carbocation might proceed via SN1 reactions. Okay, so just to put that in a brief summary, the nature of the carbocation will be important for deciding if the reaction can occur via an SN1 reaction, if it can form a stable carbocation, for instance, because it can form a tertiary carbocation with extensive hyperconjugation, or it can form a carbocation that can be stabilised via resonance, then that's likely to occur and we're likely to get an SN1 reaction. If you can't form a stable carbocation, we won't get an SN1 reaction, we'll get an SN2 reaction. Now, steric effects are also important because, again, if we go back to those generic reaction mechanisms which I asked you to learn, in the SN1 reaction, what we're seeing is we're losing the leaving group first. So that means if we've lost one group from the carbon, there's less steric hindrance around that carbon, so it's more likely to be approachable. Excuse me. If we have an SN2 reaction where our nucleophile is going to attack before the leaving group departs, that's going to be introducing extra steric hindrance at that key step of the mechanism. So what we find is if we have a substrate which has got not much steric hindrance around it, so here we would just have a carbon with 3 hydrogens, then that means it's going to be really quite easy for a nucleophile to approach that, and we're more likely to get an SN2 reaction. So here the SN2 reaction is going to be very fast. If you go to the other extreme, if you had a molecule like this where the carbon has got 3 methyl groups on, X is our leaving group, by the way. So here we've got a carbon with 3 methyl groups on with a leaving group. The chance of a nucleophile attacking here in an SN2 reaction before this departs is going to be really very low because there's a lot of steric hindrance. There's a lot of bulk, a lot of electrons which are stopping the electron-rich nucleophile from getting to the carbon to kick out the leaving group in the same step in the SN2 reaction. So in those cases, the rate of the SN2 reaction is going to be incredibly low. And then we get sort of in between. Here we've got 2 hydrogens and a methyl, so we're starting to introduce some steric bulk, so the reaction rate goes down. Here even more so, we've got 2 methyls, so the reaction rate goes down even lower. Now this means therefore that where we've got less steric bulk, we're going to get more likely to have the SN2 reaction. Where we've got more steric bulk, we're less likely to get the SN2 reaction, we're more likely to get the SN1 reaction. And notice here that this is exactly as we've said on the previous slide, you know, the two phenomenons, the steric effects and the stabilisation of the carbocation, work together to give the same outcome. So here where we would have a tertiary substrate, we saw on the previous slide that tertiary gives a stable carbocation, so it's likely to occur via SN1. That's what we're seeing here. It's still likely to occur via SN1 because the steric bulk of the substrate means it's unlikely that the nucleophile could attack before the leaving group departs via the SN2 reaction. Okay, so we've looked at carbocation stability, we've looked at steric effects. The next thing we're going to think about is the nucleophile. So we've seen for the different rate equations for the SN1 and the SN2 reactions that they're different. One is unimolecular for the SN1, one is bimolecular for the SN2. So the only mechanism that involves the nucleophile in the rate determining step was the SN2 reaction. Remember again that generic SN1 reaction that you've hopefully drawn out. The rate determining step for that does not involve the nucleophile. It only involves loss of the leaving group from the initial molecule. So if the nucleophile is only involved in the rate determining step for the SN2 reaction, it means that for that reaction, we could make the reaction more effective by having a higher concentration of the nucleophile or by having a better nucleophile, a stronger nucleophile in the first place. So for SN2 reactions, if you've got a strong nucleophile, the reaction will be promoted. If you've got a higher concentration of the nucleophile, the SN2 reaction will be promoted. The nucleophile will not affect the rate or the efficiency of the SN1 reaction at all because it is not involved in that first rate determining step. So in terms of what makes a strong nucleophile, what makes a good nucleophile, nucleophilicity is influenced by the size of the attacking atom in the nucleophile. If we look at the same group in the periodic table, that's because as you go down the periodic table and the atom becomes larger, the electrons which we're trying to use in that bond forming process are further away from the nucleus, so they're more available for donation. So if we wanted to promote an SN2 reaction, and we wanted to use a strong nucleophile, we could think about using a nucleophile which is large, which is towards the bottom of the group in the periodic table, because that will be able to lose its electrons and make the bond easily in the rate determining step. Now, if we think about the leaving group, actually the leaving group is important for both the SN1 and the SN2 reactions, because if you go back to those generic reaction mechanisms, you'll see that in both of the rate determining steps, the substrate is losing its leaving group. So if it's losing the leaving group in the rate determining step, the better the leaving group, the more likely it is to be lost from the molecule, the more likely we are to get on with the SN1 or the SN2 reaction mechanism. So again, if we think a little bit about what makes a good leaving group, so if you have a good leaving group, it means that the bond, the R to the leaving group bond, has to be quite weak so that it can break away easily. We want to have a nice polarized bond so that the electronegativity differences are quite large, so that the leaving group is already pulling the electrons towards itself, breaking that bond so that the strength of the bond is weakened. We can think about the stability of the leaving group. Is it stable as an anion? And we can also think about how we might be able to stabilize the anion through solvation. So all of these would help us to make the leaving group a very good leaving group. And if you make that leaving group a very good leaving group, it means we will encourage both the SN1 and the SN2 reaction to occur, because both of those see loss of leaving group in the rate determining step. Okay, so the last factor that I said we would look at is solvent effects. So the solvent is what we are dissolving our reactive species in when we're doing the reaction. And what we find, again, is we can relate the discussion on this slide back to the mechanisms that we saw, the generic reaction mechanisms. So I've said this many times now, for the SN1 reaction, what we're doing is we're forming a charged carbocation in that rate determining step because we're losing our leaving group. Now, if we're forming something which is charged, a carbocation is charged, that's polar. And what we find is like dissolves like. So if we have a polar charged intermediate, that will want to dissolve in a polar solvent. Polar meaning that it could have a proton if it's a protic polar solvent, or it might not have a proton in the solvent if it's aprotic. So these are just specific details if you're going to try and do the reaction in the lab yourself at a later stage, maybe in your 4th year research project. But if we wanted to do an SN1 reaction and we wanted that to be efficient and to be the favoured reaction, we'd be wanting to have something which will stabilise the carbocation, and we would be using a polar solvent. Now, in contrast, hopefully again this is becoming quite familiar to you, for the SN2 reaction, we've seen that we do not form a charged intermediate. We proceeded via transition state. So in theory, you could say, well, for that transition state, it isn't charged, so we probably don't need a particular polar solvent to encourage that reaction because it's not forming a charged species in the way that we did for SN1, and that would be correct. However, what we find is that the nucleophile which is involved in the rate determining step is often going to be solvated if you have a polar protic solvent, and that would reduce its nucleophilicity. So what we tend to do is we want to use polar aprotic solvents. So it's sufficient to dissolve the nucleophile which is charged in the first place, but it isn't so polar that it's going to solvate the nucleophile and make it unreactive. So the key point here is for SN1 reaction, we would want a polar protic solvent, whereas for the SN2 reaction, what we'd be wanting is a polar aprotic solvent. It's sufficiently polar to dissolve our nucleophile, which is charged, but it's not protic. It's not going to solvate the nucleophile and mask it by solvent molecules, so it can't react. So when we're doing reactions, it's often possible to literally swap the mechanism from being SN1 to SN2 and vice versa by changing the solvent in which we do the reaction. So if we wanted to have a SN1 reaction, supposing we wanted to make a mixture of enantiomers for our drug discovery process, we could do this in a polar protic solvent. If we wanted to do an SN2 reaction, because we knew the mechanism that we wanted was the one that gave us a single isomer, then we could do our reaction in a polar aprotic also meaning non-protic solvent. So that would just be a simple trick that we can do to influence which mechanism occurs, SN1 or SN2. Okay, so the last thing to say, we've covered everything now that you need to know for nucleophilic substitution reactions. The last thing to say is that although we've looked at ways in which we could bias SN1 over SN2 and vice versa, there is another reaction that actually competes with the nucleophilic substitution reactions, which is another thing that we'd have to think about when we're doing our reaction. Are we definitely going to get a substitution reaction, or could we get this competing reaction? The competing reaction is an elimination reaction, which I introduced at the very beginning of the lecture series. So what we're going to do is leave it there for now, because we've covered everything we need to know for the SN1 and the SN2 reactions. And next time we're going to move on to look at the elimination reactions, noting that not all nucleophilic displacement reactions proceed so as to give 100% yield to the desired product. Often we'll get elimination occurring as well. And it's something that we can think about in terms of mechanism, and we can think about in terms of how we control whether we favour a substitution reaction or an elimination reaction. Okay, so yeah, go through the mechanisms, check at this stage you're really happy with the generic SN1 mechanism, the generic SN2 mechanism. You can understand the stereochemical consequences. Make sure you understand why it's important that we know which isomer we're making, and also think about those factors that we've just gone over, which will help us to influence whether we make the SN1 or the SN2 reaction most likely.